We now go back into the earlier part of the book briefly to talk about section 8.5. This is our introduction to functions and function notation. Many of these concepts I expect will be fairly familiar from previous classes. First, we'll start with some definitions. A relation is just a set of ordered pairs of real numbers. For instance, I have this relation. 0, 1, 2, 4, 4, 6, and 4, 1. The domain of a relation is the set of all of the first coordinates in the relation. So if I look back at this relation, its domain is all of the first coordinates. Here's 0, 2, 4, and 4. I don't include duplicates in a set. So when I write down D, my domain, I just have 0, 2, and 4. So those are all of the first coordinates. As you might expect, since we just talked about our first coordinates, we now have our second coordinates. The range of a relation is the set of all of its second coordinates. So let's go back and look at our relation. My first coordinates were 0, 2, 4, and 4. Now I have 1, 4, 6, and 1. 1, 4, 6, and 1, so I just have my range is equal to 1, 4, and 6. R equals the set 1, 4, and 6. When you have a list of ordered pairs, fairly easy to identify. We list the first coordinates, those are our domain. We list the second coordinates, those are our range. We can also do this if we have a graph. When I'm thinking of my domain here, I'm thinking of all of the x values. Remember, this axis is your x-axis. Sometimes called your domain axis. Nobody actually says that, but textbooks sometimes do. Here's your y-axis. So your x-axis has to do with your domain, your y-axis has to do with your range. So I want to think of which x values I can plug in. When my x value is 1, certainly I can plug that in, see where I am on the graph. I'm kind of near -2. So that's definitely in my domain. Similarly for -1. So I know all of the values between -3 and 3 are in my domain. So I'll say D is equal to everything from -3 to 3. These brackets, the square brackets, mean that I am including my endpoints. If my graph didn't have these points at -3 and 3, then my domain would be -3 to 3, but not including the endpoints. That would mean that I could plug in everything from -3 to 3, but not either -3 or 3. Similarly, we can think about our range. Our range is what gets hit when we plug in these domain values. So when my x value is 0, if I plug that in, I get a y value of -2. So -2 is definitely in my range. Similarly, I can plug in an x value to get that y value of 0. So that's in my range. And all the way up to -2. Sorry, to +2. So my range is all of the values from -2 to +2. If I have these open circles here, that means those points are not actually included, so I will have an open bracket there. If I had the solid filled in circles there, like I had initially, then my range would be from -2 to 2, because those points would be included. So I can look at a graph and I can decide what my domain and my range are. but that might not be finite, right? Here, when I think about what x values I can plug in, it's a parabola. It goes on up forever. I can plug in any x value, and I'll get a y value out. I have a lot of notations for that. I could say that my domain is fancy R. That means all real numbers. Or I could say that my domain is the interval from negative infinity to infinity. That's perfectly allowed. My range, though, no x value that I plug in is going to get me out the y value negative 8, or negative 10, or anything below negative 7. So my range is just negative 7 and up. So negative 7 and then all the way up to infinity. Whenever you have an infinity, you will always have an open bracket, since we can never get all of the way to infinity. Okay? Now, we said we were talking about functions and function notation, and we haven't talked about functions yet, so we'd better get there. A function is just a relation in which every domain element has exactly one corresponding range element. So let's look back at the relation that we used to have. We remember domain, we said that was 0, 2, and 4. So I want to make sure that every one of those domain elements has exactly one corresponding range element. But I have a problem. My problem is 4. Here's 4 in my domain, and here's 4 again. And their range elements are not the same. So 4 has 2 corresponding range elements, 1 and 6. So that tells me this is not a function. Let's look at another one. Here's a relation. Let's figure out what our domain is. Domain is the set of all first coordinates. So there's 2, 3, 4, 5. 2, 3, 4, 5. Now our range here is just 3. However, every domain element has exactly one corresponding range element. I never have one domain element that points to 2 range elements. So I'm fine. This is a function. It seems like it shouldn't be, because there's one element in the range. However, this will come up again an oddly large amount of time later in the semester. Oh wait, crap. That's actually a part that we cut from this class because we lost it. Because we lost that week. This won't come up again. But this is a function because every domain element points to exactly one corresponding range element. There is a concept when we talk about the reverse. In this case, every range element definitely does not have exactly one corresponding domain element. But we're not going to worry about that for this class because we don't have time. Alright. So we have an easy way when we're looking at a graph to immediately be able to tell whether it's a function or not. If it is possible to draw a vertical line that touches your relation at more than one place on its graph, then your relation is absolutely not a function. So if I look at a relation like this, it's a nice parabola. No matter what vertical line I draw, I have technology that allows me to draw straight vertical lines. That's magical. No matter what vertical line I draw, it's going to cross my graph in exactly one point. So that is a function. We can compare that to something like this weird relation. I can easily draw a vertical line through this that crosses it in lots of places. Way more than one. So that is not a function. Now my last important thing is I want to be able to find the domain of a function when I'm just looking at an equation of a function. The domain of a function like this is all of the points that I'm allowed to plug in for x. So let's think about 2. Is 2 in my domain? I can plug it in for x. 2 minus 1 over 2 plus 2. That's 1/4. Sure, I was allowed to plug 2 in. That went great. How about 3? 3 minus 1 over 3 plus 2. 2/4. 1/2. I'm allowed to plug most numbers in, but not all numbers. Let's say I want to plug in -2. If -2 minus 1 over -2 plus 2. That is, I have -3 over 0. That's a problem. One of the few solid mathematical rules is you can never divide by 0. Anything divided by 0 is undefined. So I can't have this. So -2 is not in my domain. Since -2 is the only thing I can plug in that will make my denominator 0, it's the only thing that's not in my domain. So my domain is everything except. I have some notations for that. I can just say x is not equal to -2. Or I could say my domain is everything from -infinity to -2, but not including -2, and -2 to infinity, but not including -2. Those are good notations. This is why this section is included at this moment. How we got that -2 was by thinking, what makes this denominator, x plus 2, equal to 0? Certainly, x is -2. But what if I had something more complicated? Let's say I had x over x squared plus 3x plus 2. In order to find the domain, I need to know when is x squared plus 3x plus 2 equal to 0. And that's hard. And that requires factoring, which is what we're about to learn in the next chapter. As soon as I tell you that x plus 1 times x plus 3 is the same as x squared plus 3x plus 2, now you can determine when is x plus 1 equal to 0 and when is x plus 3 equal to 0, and now you can find your domain. I want x to be not equal to -1, -1 or -3. And my domain is everything but that. But I need the ability to turn this into this. That's factoring. And we are about to start getting techniques for it.